Hi, my name is Peter Hurtík, and this is tutorial how a driver assistance software can be easily designed and implemented. This movie is submitted to the webinar competition organized by IEEE Computational Intelligence. Nicolas Madrid is the co-author of the original work published in the journal. At first, I will explain what driver assistant is. We consider a device which will be mounted on the windshield and will be monitoring a road. If a car departures a lane, the system should signalize some warning. Of course, new cars have these functionalities, but usually for an additional fee. The problem is with older cars, where the system is not available. We aim especially at high roads, where there is a high probability that the driver will be tired. Goal of this tutorial is to show how the mentioned solution can be easy designed and implemented. As the system we consider a software running on a mobile phone. The main condition is easy usage for drivers. The problem can be with real-time processing. By real-time we mean at least 15 frames per second. For example, the mobile phone can handle more than 150 less instructions per second. And of course, instructions on the mobile phone are usually less powerful. Therefore, design solution has to be computational time efficient. There is our idea how to do that. At first, we want to detect lines painted on the road. For the detection, we will use half transform. Then we determine car position relative to the detected lines. And finally, if the car will be detected near some line, we will show warning. As I said, we plan to use half transform, so I will briefly show to you how it works. But first, we have to know what is the computer image. In this task, we work with two-dimensional image. The image is represented by a function, generally continuously. But in computer, we deal with discrete image function over some bounded domain. The function range is dependent on chosen framework. In this tutorial, we will work with a grayscale image or with a color image represented by RGB model determined by triplets of values. Let me remind that in two-dimensional computer image, the function element is called pixel. So, we want to detect lines on the road. Because of the task of looking for lines is computationally expensive, we use half transform. The half transform takes function domain of width and height coordinates and switch them into dual space called half space. The half space consists of coordinates of r and phi. R represents line orthogonal distance to origin and phi line slope. These coordinates come from line formula. Now we can introduce half transform algorithm. The steps are as follows. At first, we will browse all pixels in the original image. If a gradient magnitude of particular pixel is higher than given threshold, we will continue on to the next step. In the third step, we evaluate distance between pixel intensity and some intensity we are looking for. If the difference is lower than the threshold, we will continue with the next step. In the fourth step, we will browse all combination of phi, and if the fifth step, we will compute r for the given phi and pixel coordinates. The computed r is used in the sixth step, where so-called accumulator value for particular combination of r and phi is incremented. After processing all pixels in the image, we will browse all accumulators in the seventh step. Eighth step evaluates particular combinations, and if some accumulator value is higher than a threshold, we found a line that we can paint into image. As example, we have an illustration of the algorithm. We can easily say that we found 3 points satisfying gradient and intensity conditions in the image. For the given points, we compute all r and phi coordinates. A point in image is in half space illustrated as a curve. After browsing all 3 points, we evaluate dual space and we can see that we found an accumulator where all 3 curves intersect together. The found coordinates of r and phi describe our line. So, now we can detect lines on the road. The question is how the design algorithm works. The answer is it is not ideal. Let us consider image below. In the image we can see that some problems can appear. The line can be covered by some shadow. Then the line has lower gradient magnitude and also intensity is different. Or the dashed line will not be detected correctly because of the accumulator value will be small. Or there can be some foreign objects satisfying gradient magnitude and intensity conditions. The point is that the shown image has some issues. I will show 2 of them. The first issue is how to determine intensity of a homogeneous area. The known fact is that the rectangle on the right side has intensity 140. The question is, what intensity has the rectangle on the left side? If you will look to the images from the far distance, they will look the same. But if you implement algorithm to choose only intensity 140, you will fail. The reason is that the area is not homogeneous, as you can see on the zoom picture. It consists of intensities 130 and of 150. The intensities interact, and that leads to difference between human observation and computer behavior. Similar problem is illustrated on the second issue. Author of this picture is Bach-Atelson. The question is if the two rectangle intensities are the same. For the people not, because again, people interact with surrounding colors. In fact, the intensities of the rectangle are the same. Again, we have difference between human and computer behavior. The difference appears because we don't take context of pixels into account. In this section, we will try to solve our problem of image issues using fuzzy approach. Let me repeat that computer two-dimensional image is represented by the function over discrete domain, where the element is called pixel and the pixel value is the crisp value. The fuzzy set is extension of a set where we replace the characteristic function by a membership function. The answer to the question if some element belongs to the set is in the case of the set yes or no. In the case of the fuzzy set, the answer can be something between yes and no, mathematically in the interval of 0 and 1. The common use fuzzification of the image lie in usage of interval of 0 to 1 as the function range. The value is assigned by taking a real number instead of integer. In my opinion, this naive approach is wrong because it only rescales the range and doesn't bring any new information. We propose our own image fuzzification. We want to replace each pixel crisp value by a fuzzy number. The fuzzy number is a special case of the fuzzy set. For the sake of simplicity, we will use fuzzy numbers with triangle membership function. The illustration of the triangle membership function is shown on the figure below. You can see that you can define the function using three values a, b, and c. The question is how we can obtain these three values. We know that we should use pixels that are somehow surrounding particular pixel, and moreover, we can look for inspiration in human behavior. Here we have a picture. If I ask you what is on the picture, you'll probably answer that there is some wall, some road, trees, field, and so on. But the answer that in the center of the field is a cat is not so common. The reason is that your attention is focused on objects which are different than others. Objects which are emphasized somehow or with extremal colors and so on. So from that, we can take inspiration and we can use extreme values from pixel surrounding. Now, we can formally define pixel neighborhood. It is an area over the pixel where distance between it and an arbitrary pixel in this area is smaller than delta. Therefore, we will call it delta neighborhood. As a left border of the membership function, we will assign minimum pixel value inside delta neighborhood. Dually, the right border of the membership function is maximal value inside delta neighborhood. And the membership function core will be connected with the value of center pixel of the delta neighborhood. Using the three obtained values, we can define membership function using this formula. Moreover, using this formula, we can compute arbitrary pixel membership degree into mentioned fuzzy set. Finally, we can make definition of our structure. Image represented by a fuzzy function is a structure where each pixel of the original image function is replaced by a fuzzy number. Again, here is the illustration how the fuzzy number for corresponding pixel is created. There we have image over the mentioned domain. We will browse all pixels in the image. For illustration purposes, we will now use the pixel which is marked by the red color. We establish delta neighborhood around this pixel. The delta neighborhood is marked by the red rectangle. Now we will construct the fuzzy set. Because we are processing the delta neighborhood for the center pixel, the pixel value has the maximum membership degree, 1. We then search for the minimum and the maximum pixel value and use them as the left and the right border of the fuzzy function. From that, we establish fuzzy function with triangular membership function. Now, we can revise the computer image issues. In the homogeneous area, we have not case value of 130 and 150, but two fuzzy sets. The membership degree of intensity 140 is for both fuzzy set 0.5, so we can interpret it as, yes, your considered intensity is there, but the area is not as homogeneous as you think. How is it in the case of optical illusion? Again, instead of crisp values which are equal, we have two fuzzy sets. You can see that the cores of the fuzzy set are the same, but their supports are different. This can be interpreted as, yes, the intensity are the same, but they look different. Now, we'll try to modify the half transform to work with the proposed structure. Before modifying half transform, we define the last missing part to work with image represented by a fuzzy function. The last necessary part is gradient operator. Because gradient magnitude can be taken as a variation inside the image function, we can define our gradient magnitude easily. The variation is in our case described as the size of support, and therefore the gradient magnitude is computed as the support size or as a difference between right and left border of the membership function. Now we have all preliminaries and we can modify the algorithm. In the first step, we create image represented by a fuzzy function using proposed algorithm. Then we will browse all pixels in the image. In the third step, we control the gradient magnitude using proposed gradient magnitude operator. In fourth step, we evaluate membership degree of the intensity we are searching for, and if it's bigger than the threshold, we'll continue. In the fifth step, we browse our combination of phi, and in the sixth step, we compute R for the given phi and pixel coordinates. The computed R is used in the seventh step, where the accumulator value for particular combination of R and phi is incremented by the membership degree. After processing all pixels in the image, we'll browse all accumulators in the eighth step. In the ninth step, we evaluate particular combination, and if some accumulator value is higher than the threshold, we found a line and we can paint it into image. So you can see that the difference to the standard algorithm is in the first step, where we create fuzzified image. Then in the third and fourth step, where we work with our structure, and finally in the seventh step, where we increment accumulator membership degree. Using the proposed algorithm, we will design our driver assistant application. Before we can use our algorithm, we have to focus on the device. We will use Android mobile phone. The access to the camera is through SDK, so it's no problem. Because the Java on Android is slower than native implementation, we will use Java for application itself, but the algorithm will be implemented in C++ through Java native interface. Of course, we have to take into account factors like variable camera position or variable light conditions. From the propositions, we can vary particular step of the application. In the first step, we obtain image from the camera and decode it from native format into grayscale image in the second step. Then, using C++, we resize the image into our working resolution. In the fourth step, we create our structure and use it in fifth step, where we apply design modified half transform algorithm. The detected lines on the road are painted in the sixth step. The output is returned back to the Java part, and using SDK we displayed it in the seventh step. In the eighth step, we make a decision if we are crossing a line. From the decision, we can adaptive modify threshold in the ninth step. After that, we repeat the algorithm in a loop. After implementation, we can verify our algorithm abilities. In our implemented test, we measured that the algorithm based on modified half transform is about 60% faster. And what is more important is that it is more robust. The original algorithm has bigger problem with lines, which are covered by a shadow or are damaged. When we set both algorithm thresholds to work similarly, the modified algorithm was more accurate in these cases. Furthermore, we can improve our algorithm to be faster and more accurate. In the half algorithm, we use trigonometric function. We can pre-compute their values to make algorithm faster. To make algorithm more accurate, we display warning after confirmation of 3 consecutive images. Also, we can focus on smaller area, make threshold adaptive, we can downscale images, etc. After evaluation of our algorithm on a standard Qi mobile phone, we obtain average computational speed of 18 frames per second. If we work with 3 confirmation images, our delay between situation and warning is in high road car speed about 6 meters. This is good result. Here are screens of how our application output look like. To make application more user-friendly, we can implement several other features such as, instead of painting a lot of lines, we can paint area as a hull of lines. This area represents the road. The signalization can be presented by color of the road and by audio warning. With control of amount of confirmation images, we can change signalization delay. We can use mobile GPS and show GPS speedometer. The switch to the full screen of displayed video can be implemented to arrange system better. And finally, we can record the video in a loop to be used as a black box. Here is the screenshot of the final application running on the mobile phone with previously mentioned improvements. We can display the configuration window and control threshold parameters. On the video part, we can visualize the road with in-painting tracking. Also, by click on that video, we can bring it to the full screen mode. And here are several pictures showing the system in real traffic. So, this is the end of this tutorial. We demonstrated 2 aspects. The first one is how a well-known algorithm can be modified if we take into account human behavior. The second aspect is how this modified algorithm can be placed into whole application and used as a real-life device. For more details, you can visit us on our website, where you can find link to download the application or several videos showing how application works. I'd like to thank these people. Nicolas Madrid, co-author of original article in journal, who helped me a lot with formal descriptions and illustrations. Martin Štěpnička and Martin Jablonský for consultations, and my wife Gabriela for the perfect atmosphere. I'd also like to thank the complete Institute group. Thank you for watching.